Hello everyone. Today, now in the last class, we have done a differentiation of parametric functions. That was easy enough. You just need to understand that parametric functions are two different type of functions. But in fact, inside parametric functions, there will be some inverse trigonometric functions as well. So what am I doing today is, first, I am teaching you how to differentiate inverse trigonometric function. Then we will move back to parametric again and solve maybe few more sums of parametric based on inverse trigonometric functions. Okay, so how would you differentiate? The differentiation of inverse functions are quite simple. You know the formula for inverse trigonometric functions, derivative. Earlier, right in the beginning, I had not given you the inverse formula. Actually, I forgot there. Then later, I gave you again. I suppose you have already copied it, but still some of you might have confusion regarding this formula. Let me explain. So remember, the derivative of sine x and sine inverse x is not same. They are quite different. Okay, so this is the derivative of inverse functions, all six. So ddx of sine inverse x is 1 by under root 1 minus x square, and ddx of cos inverse x is minus 1 by under root 1 minus x square. Did you see the derivative of sine inverse and cos inverse are almost the same? The only difference is the sign. Okay, and tan inverse and cot inverse is 1 divided by 1 plus x square and minus 1 divided by 1 plus x square. So same, just a minus difference. And then sec inverse and cosec inverse, 1 divided by under root x, x under root x square minus 1, and in cosec there will be a minus. So cos inverse, cot inverse and cosec inverse, there will be the minus. So how to remember? Very easy. All the c's have minus. Did you see that, everyone? So all the c, cos inverse, cot inverse and cosec inverse, they have minus sign in them. Just remember that. Others, they are just plus. Got it? So applying this formula, we will differentiate the first sum, that's here on inverse trigonometry. How would you differentiate? The chain rule also gets applied here. The chain rule that we have done in the first class, I think third class of differentiation, also applies in inverse trigonometric function. Correct? So let's start. So differentiating both sides with respect to x. It says derivative of sine inverse 2x. So this has to be actually x, but instead there is a 2x. So I think I'll have to follow chain rule first. So what is ddx of sine x? So I'll write here dy dx, and that will be ddx of sine inverse 2x. Can I do that? Now follows chain rule. I'll simply do for sine inverse first, the outside one, and imagine this is x. So what is ddx of sine inverse x? 1 divided by under root 1 minus x square, but my x is 2x, into ddx of the leftover, that's 2x. So that gives me 2, and because ddx of 2x is 2, and then under root 1 minus 4x square. Is that correct? So that's how we differentiate the inverse function. Quite simple. Okay, so remember, the chain rule that we have done earlier also applies to inverse trigonometric function. Is that correct? Okay, let us move to another sum. Here I have another one, the second one. How would you differentiate this? Find dy by dx. So again, differentiating both sides with respect to x. So here comes the operator dy by dx, and here ddx of tan inverse sec x plus tan x. So clearly, again, I think I'll have to apply chain rule because this is function inside a function. So first I'll only do for tan inverse. I'll do the outside one. What is ddx of tan inverse x? Let me write it down here. ddx of tan inverse x is 1 divided by 1 plus x square, isn't it, everyone? So that'll be 1 divided by 1 plus x square. This is my x here. Okay, let me show you. This is x, everything here. So it'll be tan sec x plus tan x into, now chain rule, ddx of, what do you have? Sec x plus tan x. Correct, everyone? Okay, now let me do it here. Let me write a little small. So what do you get? I get 1 divided by 1 plus, let's expand this, will be a square, that's x square x, plus b square tan square x, plus 2 sec x tan x. Correct, everyone? Okay, into ddx of sec x is sec x tan x, and ddx of tan x is sec square x. Correct? Okay, great. That leaves me here 1 divided by, everyone knows 1 plus tan square is sec square x. So you know that 1 plus tan square x is sec square x from trigonometric identities. So sec square x and one more sec square x here gives me 2 sec square x. Let me repeat. 1 plus tan square x is sec square x, plus one more sec square x will give you 2 sec square x, correct? Plus 2 sec x tan x. Okay, that here I can take common. What's common in the circled one here? Sec x common. Sorry, there shouldn't be equals to, into, and tan x plus sec x after taking common, because sec is out and one of the sec comes out. Okay, what I can do here is 1 divided, I can take 2 sec x common even here, the highlighted one, do you see here? So take out 2 sec x of tan, you get sec x plus tan x, and you also have here sec x tan x plus sec x. So clearly you see the tan x plus sec x, the tan x plus sec x gets cancelled. And what should be your answer? Let me rub this a little here, so maybe I'll do it here. So what will be the answer, everyone? So the answer is sec x, and sec x also gets cancelled, by the way, so the answer is half, interestingly. So what's the answer of this? What's the derivative of a tan inverse sec x plus tan x? Simply half. That's the leftover, isn't it? Here we have the third sum. Now this is quite interesting. Now differentiate, you need to find the derivative of half sine inverse 2x divided by 1 plus x square. You may think maybe I will directly differentiate, like I'm just showing you, dy dx equals to half out d dx of sine inverse and then 2x divided by 1 plus x square. So that way this is considered as x, and then you may have to apply the chain rule. First do sine inverse, then do this one, and to do this one, this highlighted portion, you have to use quotient rule, and it will become very, very lengthy. So I rather not prefer this method. What will I do instead is, if you remember, we had once discussed about this standard substitution table. Remember this? Yes. So inverse functions can be simplified to very simple algebraic functions, sometimes a complicated inverse function. So what we are going to do here as well is, we are going to simplify this inverse function, as you can see here, and make it simple first. Okay, so first of all we'll learn to simplify this. Only after it becomes simplified, then we will differentiate it. Remember, that's why we learned simplification of inverse trigonometric functions in the previous chapter. That is in the chapter inverse trigonometric function, correct? Now I need to put correct trigonometric substitution to simplify this. So what is my objective now? Check this out. So I have y equals to half sine inverse 2x minus 1 plus x square. I need to substitute x in such a way here that this 2x and 1 plus x square, when you replace this, should give you sine, something in terms of sine. Why? Because if it gives you sine, then sine inverse and sine of something, let's say something, will get self-adjusted, and you are just left with this quantity. Are you getting the point, everyone? So this should be very carefully substituted. X should be very carefully substituted so that the highlighted portion gives you a sine function. What should you give everyone? Sine function. Had this been cos, the outside one, then you would want cos. Had this been tan, then you would want tan here. Are you getting the point? Tan inverse. So that way it works. So if there is a sine inverse, you want sine because it's self-adjust. If there is a cos inverse outside, then inside you want cos. If there is a tan inverse, then ultimately you want here tan. That's how it works. Okay, so carefully substitute so that so that this function gets simplified. Okay, so let's see the substitution table. Is there a substitution for 2x and what was it? 2x 1 plus x square. Yes, indeed. Did you see this, everyone? See the highlighted one here, 2x 1 plus x square. If you ever have 2x 1 plus x square, you can substitute x equals to tan theta. It's written here. Okay, so let's go back and make our necessary substitution. So let x equals to tan of theta. Why tan theta works? Because 2 tan theta divided by 1 plus tan square theta in trigonometric is the trigonometry is the formula of sine 2 theta that we have done in class 11. Okay, so when I do that, I get y equals to half. There's a sine inverse. Look carefully. So 2, what do I replace instead of x? Tan theta divided by 1 plus tan square theta. Correct? And what does this mean, everyone? It means sine 2 theta. So y equals to half sine inverse sine 2 theta. Correct? So sine and sine inverse get self-adjusted. Y will be half into 2 theta. Okay, because it vanishes. This one vanishes. So 2 and 2 gets cancelled. So ultimately you are getting y equals to theta. But theta is something that you theta is a bridge variable. You supposed x equals to tan theta. So what will be theta in terms of x from here? So I can say theta equals to tan inverse x if I flip it, isn't it, everyone? If x equals to tan theta, then theta should be tan inverse x. Okay, so replace y equals to tan inverse x. Now finally I have simplified this complicated function to this one. So y was actually half sine inverse 2x divided by 1 plus x squared, but instead I can also write it as y equals to tan inverse x. Now differentiate. So differentiating both sides with respect to x, what do you get, everyone? With respect to x, I get dy by dx equals to ddx of tan inverse x. What is ddx of tan inverse x, everyone? ddx of tan inverse x is 1 divided by 1 plus x squared. So that is the answer for this particular sum. I hope you have understood this. So how did we simplify our inverse trigonometric function? We didn't directly differentiate it. We simplified it first and then we differentiated it with respect to x. Okay, what about y equals to tan inverse 1 plus x square under root minus 1 plus x? What would be the necessary substitution for this sum? What should I replace x so that this gets simplified first? So I don't think I have this term in the table. You can go and look at the table. I don't think you have this term exactly in the substitution table. Let me show you. No, I don't have it. If you see it carefully, I don't have this in the substitution table. So what am I going to do is I'm going to think about something that will make the highlighted expression into tan, because I would want tan out of this, because tan inverse and tan will get self-adjusted. Remember that. So replace x in such a way that everything that's highlighted in blue will give you tan. So what will I do? So I see that there is a 1 plus x square inside the root, isn't it, everyone? And according to the table, substitution table, if you ever have a square plus x square category here, then what can I do? I can replace x by a tan theta. Coming back to the sum, so I can say let x equals to tan theta. Can I do that, everyone? Because once I use tan theta, the square root gets simplified. So theta will be tan inverse of x. So what can I say? Y will be tan inverse, open bracket, under root 1 plus tan square theta minus 1 divided by tan theta. Look carefully. Is that correct, everyone? Okay. That gives me y equals to tan inverse. What is the formula of 1 plus tan square theta? Everyone knows 1 plus tan square theta equals to sec square theta. That's by trigonometric identities. So it will be sec square theta, and there's a square root minus 1 divided by tan of theta. Correct? Okay, so further I have y equals to tan inverse, square and the square root gets cancelled, sec theta minus 1 divided by tan theta. Can I do that? Let's simplify it. It's not yet simple. Y equals to tan inverse. I can write 1 by cos theta minus 1 divided by sine theta by cos theta. Correct, everyone? Let's take LCM. Y equals to tan inverse, the LCM is cos theta in the numerator, 1 minus cos theta divided by sine theta by cos theta. I can cancel the denominators, isn't it, everyone? Yes. So I'm left with, let me do it here, somewhere here. I'm left with y equals to 1 minus cos theta, tan inverse 1 minus cos theta divided by sine theta. Am I right? Let's check. Yes, absolutely. Okay. My mistake here. Let me show you. this doesn't get cancelled. Cos theta gets cancelled, so it will be 1 minus cos theta divided by sine theta, remember. Okay, so I have cancelled with cos this, and let me highlight cos theta, and cos theta gets cancelled. Okay, this remains sine theta. Okay, come back. So I have now my motive was to get tan out of this circled one, isn't it? So I have still the ratio is still in the fraction is still in cos and sine. So what do? And now I'll have to use the half angle formula. If you remember, what's the half angle formula of 1 minus cos theta? 1 minus cos theta divided by 2 in trigonometry is sine square theta by 2. If you remember, check out the formula from class 11. And if you know, 1 plus cos theta divided by 2, just for your information, is cos square theta by 2, correct? And what is the formula of sine theta? It's 2 sine theta by 2 cos theta by 2. If you remember, these are the half angle formulas. I've given you 3 here just for reference. Okay, so I can write it as 2 sine square theta by 2, because this 2 goes here. Okay, divided by 2 sine theta by 2 cos theta by 2. Which formula did I use? These two formulas, the highlighted ones. Check this out. These are the formulas I've just applied. 2 and 2 gets cancelled. One of the sine theta by 2 and one of the sine theta by 2 gets cancelled. So y equals to tan inverse sine theta by 2 divided by cos theta by 2. Check this out. So that gives me ultimately tan inverse, interestingly, tan theta by 2. Check this out. So whatever substitution I have made, that was absolutely correct, because I got tan here. Did you see that? So tan inverse and tan gets self-adjusted. You'll end up in y equals to theta by 2 ultimately. What was theta? Y equals to half out. What was theta, everyone? What was theta? Theta was tan inverse x. Check this out, isn't it? So let's come back. So theta equals to tan inverse x. So now differentiating both sides with respect to it. Did you see, everyone? I had the patience to differentiate it right now only. So I didn't differentiate it earlier. Earlier everything was just about simplification. When you get your ratio in a simplest form, then you differentiate. Okay, so I get dy by dx equals to half ddx of tan inverse x, and that gives me half into 1 divided by 1 plus x square. So the final answer simplified. Some of you have a habit of leaving the answer just like this. You simplify it. It will be 1 divided by 2, 1 plus x square. Just multiply and make it simple. So that's the final answer for this particular sum. That is, what was the sum, everyone? That was y equals to tan inverse, sorry, not this, y equals to tan inverse 1 plus x square minus 1 divided by x.